Hi everyone. In this video, we'll continue our discussion of the important value theorems that come as a result of continuity. In particular, in this video, we'll be looking specifically at the extreme value theorem, understanding its hypotheses, looking at a generalized version, and concluding with a proof of the extreme value theorem. In the previous video, we presented this statement of the extreme value theorem. So if f from the closed interval AB into R is continuous, then there exists, and I'll sort of summarize these two simultaneously, there exists an x sub little m and an x sub capital M, both in the interval AB, such that f sub little m of x is equal to the minimum value of f of x on the interval AB, and f of x sub capital M is equal to the maximum value of the function f of x on the interval AB. So as we think about this theorem, the sort of picture we want to have in our head is essentially the following. So I have a continuous function on a closed interval. And in fact, let me change this picture ever so slightly to make it to emphasize one particular aspect. So let me actually do this. Yeah. So on this closed interval AB, our function will achieve its maximum and its minimum values. That's what the extreme value theorem says. So there is a value here, which we might call x sub capital M, which is the value in the domain where our function achieves its maximum value over the interval. Similarly, there is a value x sub little m, in this case, that appears to be at the right boundary point of this interval, so that my function at that value achieves the minimum value of the function over that interval. Now, it's fairly straightforward from here. So given this picture, it's fairly straightforward from here to start constructing examples to see how things would go wrong if you started, for example, playing with this condition that x be from a closed interval AB into R. So if, for example, I did not require the interval be closed, then you can imagine just taking this function, keeping it exactly the same, except it's no longer defined at B. Now this value x sub little m is no longer in my domain. So if I'm now considering my domain to be the half open, half closed interval here, then the minimum value here, if I look at the set, the sort of set of all values f of x, so that x is in my domain, this set is now bounded below. So it does have an infimum, right? These values aren't unbounded below, right? They don't run off to minus infinity. So they are bounded below. There is an infimum, but that value is never achieved at any particular point in the domain. So in this case, what I've done is I've sort of eliminated the closed piece of this this interval. This set is no longer a closed set, and therefore now I have the extreme value theorem failing. Now the other way I could force this to fail is if instead of I could still look at a closed set, but I could look at an unbounded closed interval. So if, for example, I let my domain be a to infinity, then, as you can imagine, I could then take some sort of function that looks like this. Okay. And so now in this case, by eliminating the boundedness part, I still have a closed interval. This is still closed. It still contains all of its limit points, but it's now closed and unbounded. Now in this case, I don't even have an infimum for this set. This set R is unbounded below. There is no infimum. So even hoping to find an x sub little m such that this is satisfied, it's going to be problematic because there's not even an infimum over here for it to be equal to. Okay, so we can start to sort of break this, but what we see is that in the cases that we break it, what we're really doing is we're either eliminating it being closed or we're eliminating it being boundedness, or sorry, we're eliminating it being bounded. At no point are we really using the fact that this set was an interval. We're using the fact that it was closed and bounded, which makes us start to believe that we might be able to generalize this theorem to a setting where instead of just looking at a closed and bounded interval, maybe I could just look generally at a compact set X, right? So for our purposes, if we're looking at subsets of R, right, closed and bounded is equivalent to compact by the Heine-Borel theorem. And so we sort of think maybe what we really need is a compact set, not a closed and bounded set. Or sorry, not just a closed and bounded interval, right? So before I go any further with that, though, I might try. So what's an example then of a closed and bounded set or a compact set that's not an interval in R? Well, just take the union of two intervals, for example. So you start to think about, well, what if I had, say, AB, picked up the wrong color here. So what if my domain was AB union CD? Okay, so this is at least not a singular interval, right? It's a union of two intervals, and maybe actually let's union on one more isolated point E. Okay, so let's come over here, and again, we're just sort of experimenting right now, thinking about possibilities. Okay, so let's imagine now my domain. I now have my function, which is I've got AB, have AB, I'm going to have C, D, and then out here I'm going to have some point E. Okay, and so now I'm imagining my function maybe now as it's defined on the closed interval AB, union the closed interval CD, union a single value at E. Okay, does the extreme value theorem, and this is just for one example of a function, and so let's see, does the extreme value theorem hold here? So is there some value where I achieve my minimum? Now it appears that the answer is yes, that's over here at E, right? So here's my x sub little m, because there's the minimum value of my function. The maximum value of my function looks like maybe it's achieved here at D. But it looks like both my maximum and minimum are achieved. And as you start to think about it, at least for unions of things like unions of intervals, of closed and bounded intervals, seems like you should be able to do this, right? Because you should be able to sort of do it on each interval and then just pick the largest and the smallest one from each of the individual intervals. The points then are either, they're just sort of specific values. So you start to think, okay, maybe, yeah, the interval piece of it isn't important. The connectedness part of the interval is not what's important. It's somehow the closed and bounded pieces that ought to be more important. So what we want to do then is try to generalize this theorem and then prove a more general version of this theorem. Now, before we do that, I want to say that this is not the approach the book takes. So the book actually proves exactly the theorem as stated on the board here. It's a perfectly good way of doing it. However, they end up using some tricks that really only work when you're using an interval and you're working, from R to R for functions that are from some subset of R to R. What I want to do is I want to prove a more general version for two reasons. One is, well, you get a stronger result because it holds in more general cases. But also the type of proof I'm going to show you actually is the kind of thing you could adapt to the most general topological version of the theorem, which I actually showed in the last video. So I actually showed in the last video the most sort of general theorem you might hope for. We're not going to fully prove that because that would require quite a bit of topology. But I'm going to give you sort of an intermediate version of the proof that is still sort of focused on the analysis parts that are important, but also gives you a flavor of how you might prove the most general version of the theorem. Now, if you've had some topology, essentially I'm going to show you a proof that would work for metric spaces, for metric topologies. It wouldn't necessarily exactly work for the most general sense, but that's okay. We don't need to prove it in the most general case. So let's talk about this. So what I'm going to do here is I want the same theorem. I'm just going to replace the closed interval AB with a compact subset of R. So let X be a subset of R, which is compact, and let F be a continuous function from that compact subset of R into R. Then there exists an X sub little m and an X sub capital M, both in my set X, such that f of x sub little m is equal to the minimum value of my function over the compact set, and f of x sub capital M is equal to the maximum value of my function over the compact set X. Okay, so this is the general theorem that I want to prove. Again, all I'm really doing here is replacing the closed and bounded interval AB with a compact subset of the real numbers. Now, as we're seeing as becoming a trend, before we prove this, we first want to prove a couple of helpful theorems that will make our proof go a bit easier. Now, I'm not going to fully flesh out all of these theorems, although I'll at least give you of the lemmas, although I'll at least give you some intuition for why this is true. Our first lemma will provide us with an alternate definition of continuity. So our current definition of continuity says that a function is continuous at a point A in the domain if A is an isolated point, or if the limit as x approaches A of f of x is equal to f of A. Now we could take that limit definition, right, and turn it into sort of an epsilon delta type definition. And so we're sort of thinking of this as an equivalent. So on the one side, we have this sort of epsilon delta type definition of continuity. And what we're proposing is this alternative definition, and these two are equivalent because we're saying one holds if and only if the other holds. So they hold precisely at the same times. Okay? So this alternative definition says a function is continuous if the pre-image of every open subset O of R containing f of A is open in D. So to first just understand what that's saying, and I'm not even going to draw this in R. This actually, you can generalize this to more abstract spaces, and sort of for drawing the picture, I think it's actually more helpful to think about it that way. So the idea is you have some point A, and it maps over here to some point f of A. Okay. And this alternative definition of continuity says that a function is continuous if at the point A, if anytime you take some open set over here, which contains f of A, so this is O containing f of A, if I look at its pre-image, right? So these are all the values in the domain D, which map into O. If when I look over here, this is an open subset of D, of my domain D. So if the pre-image of any open set which contains f of A is an open set over here which contains A, then we would say our function is continuous. Now, roughly, why does this work? Okay. Well, the idea, and again, I'm not going to write out a full proof here, but I want to give you some flavor of why this works. So let's assume first, this is if and only if, so let's assume that our open, our normal epsilon delta definition holds, and let's show that this open set version would hold. So if I take an open set over here, which contains f of A, then the idea is, actually, let's not look at generic open sets. Let's look at neighborhoods. Okay. So if I just took a neighborhood of f of A, right, I could call this like the neighborhood of radius epsilon of f of a over here. Neighborhoods are open, and in fact, neighborhoods form building blocks for open sets. So let's try this for a neighborhood first. If I take a neighborhood here and I look at its pre-image, right? Then the pre-image over here, is going to be, I don't know, whatever it's going to be. Okay. But the idea is from my epsilon delta definition, I know that there exists some neighborhood of radius delta over here, right? So that whenever I'm inside here, this maps back to live inside here, right? For every epsilon, there exists a delta, so that anytime I'm within delta of A, my output values are within epsilon. Again, it doesn't say even that this is a neighborhood. It just says that they lie somewhere inside of here. Okay. So what you end up having to do here is you have to make some sort of finer arguments about, okay, if I start with a generic open set here, I back up over here, I use the epsilon delta stuff to then help me build up the fact that this pre-image over here must be open. That's sort of the general idea, right? And then you reverse that argument. Okay, so you assume that if the pre-image of every open set is open, then you need to show the epsilon delta definition holds. You do something very similar. So you start with a neighborhood of radius epsilon. You know the pre-image has to be some open set. Since it's open, you put it's an interior point that helps you find the delta that then works to map back over here. Okay. So again, this is not a full proof. This is just a fact we're going to use, but it is a good little alternative definition of continuity that's going to be very helpful for our proof here. The other lemma that we're going to want, and we'll actually prove this, or we'll actually sketch this out in a little more detail, is that if I have a function f, which maps from some domain into R, which is continuous, and if x is a compact subset of the domain, then f of x is also compact. So we often summarize this by saying that the continuous image of a compact set is compact, right? So if I take a compact set, I map it via a continuous function, then the image of that compact set, f of x, is also compact, okay? So again, let's think about just sort of a picture here. And so here's my domain D. My function f is mapping over here into R, right? And so I have some subset over here, X, which is compact, okay? And it maps over here to some set f of x. All right, now I want to show that if x is compact and f is continuous, then f of x must be compact. All right, how do I show something's compact? I need to show every open cover has a finite subcover. So what you do is you start by taking some open cover of f of x, right? So you cover this up with open sets, and I'm actually drawing these as like closed circles, but sort of the specifics aren't important right now. We'll actually write this out in a second, but the idea is cover this up with open sets. Take an arbitrary open cover of this. Now, you should be able to take, of each of those open sets, you should be able to take its pre-image. And if for each of these sets you do that, what you get over here is an open cover of the set X. Okay. So I took an arbitrary open cover of f of x. I took the pre-image of all those open sets. That actually gives me an open cover of x. But x I know is compact. Since x is compact, it has a finite subcover. So I select a finite subcover over here, right? So maybe really I only need, let's see, I'll use, like maybe really over here I only sort of need these few they're those don't look like things that were originally in my cover, but maybe I only need like 3 open sets over here from my original open cover to cover the whole thing. So I found my finite subcover, and now I just map them back to the sets over here that they originally came from. That gives me my finite subcover of f of x. Let's write that out in words. This one's a little easier. It requires a little bit less topology than the preimage of open sets is open definition of continuity does. This really is just using the definition of compactness. So let's write out this proof now. So first we're going to start with an open cover of so this O sub n is going to be an open cover of f of x. Okay. So then we're going to claim that if I take the preimage of each of those open sets, okay, this is an open cover of x. Okay. Now, to see that it's an open cover of x, you just need 2 things. The first is that each of these is open. Well, our assumption that f is continuous and our previous lemma, since O sub n is open, then f inverse of O sub n must also be open. The preimage of an open set is open. And we need to show that it covers x. So how do we know that it covers x? Well, sorry, this should be f of capital X. This is the image of all the things that are hit when x is mapped over into R. So over here, every value of x gets mapped to f of x. Essentially here you're using the fact that this is surjective. So you're hitting the function from x to f of x is surjective. So everything over there, if you come back, everything in f of x maps back to something in x, and you were mapping all of x. Okay, so you're actually going to, in the preimage, you're going to hit everything. This is going to cover every element of x. All right, so I have an open cover here. Now, since x is compact, there exists some finite subset of these open sets which covers x. All right. So let's sort of give those finite things a name. So let's let the O sub k's, for say k goes from 1 up to capital N. This is the finite collection of things. Sorry, I need an F inverse here. So let F inverse of the O sub k's, where k goes from 1 up to N, form the finite cover of x. Well, then the O sub k's themselves must form a finite cover of f of x. Now, again, we're going to use the surjectivity here, right? I know that everything in f of capital X is hit by mapping X via f, and everything, because f inverse of O sub k is form a finite cover of X, that means every value of X is covered by one of these. So when you map them forward again, the key here is that because your function is surjective, f of f inverse of O sub k is just equal to O sub k. Again, in general, that's not true. One of the first homework problems I actually do to show that you don't in general get equality, but you do get equality if your function is surjective. So that ends up being an important piece here. All right. So the idea is just you're mapping forward and backwards to get that the image of a compact set under a continuous map is another compact set. So you take an open cover of your image, you map that via the inverse function, you map it, or you take the pre-image, it might not be an inverse function, you take the pre-image, that gives you an open cover of the subset of your domain X. Since it's compact, you take its finite subcover, and then you map that finite subcover back forward, which gives you actually a subcover of your original open cover, which is exactly what you needed to show f of x was compact. All right. Now, again, these lemmas are not central things in the study of analysis. These are much more maybe sort of topologically motivated things, but they are sort of ideas I want you to see, and ideas that might carry through to subsequent classes, and you might solidify more there. They're also just, good exercises in thinking about functions, about images, pre-images, those sorts of things. So I think they're good to see. But now we can use the results of these lemmas to prove our generalized extreme value theorem. And actually from here, the proof becomes relatively straightforward. All right. So I'm going to assume here that X is a compact subset of R, and f from X into R is continuous. Okay. So since X is continuous, or sorry, is compact, and f is continuous, well, then our previous lemma tells us that f of x is compact. Okay. Now, what does that mean? Now, this is where we're going to use the fact that we're mapping into R. So f of x is a compact subset of R. That means, by the Heine-Borel theorem, that means that f of x is closed and bounded. Now notice here, again, I just want to emphasize, we're talking about f of capital X. This is a set, right? This is the image of X under F. So this set, these are all the values you get by mapping things in X via F. That set is closed and bounded, okay? Now, closed and bounded. All right. Well, since it's bounded, since f of x is bounded, I can define this value little m, which is going to be the infimum of the set, all right, the infimum of f of x, and a value capital M equal to the supremum of f of x, and they both exist. right? Because now f of x is a non-empty bounded subset of real numbers, so it has an infimum and a supremum. All right. Now, the only thing that's left to do is I want to show that little m and capital M are both in the set f of capital X. Because if I can do that, then what I'm saying is those are values in the image, so there must be an X value that maps to them. That's what it means to be in the image. So now we want to show that these have to both be in the actual set f of X. Now, in order to do that, okay, let me just do it for the supremum case. The infimum case will be identical. So we now want to show that M is in, well, we can write this for both of them. We want to show that little m and capital M are in f of capital X. All right. Now, somehow here, I need to use the definitions here. And the idea is essentially that I want to show that little m and capital M are accumulation points of f of x. By the definition of the supremum and the infimum, they have to be accumulation points of f of x. Since f of x is closed, it contains all of its accumulation points, and therefore these points have to actually be in f of capital X. All right, so let's see, and again, we'll just work with the capital M case from here on out. Note that since capital M is equal to the supremum of this set, or I keep wanting to write it in a slightly different notation, f of capital X, for every epsilon greater than 0, there exists an element, let's call it Z, in f of capital X, such that M minus Z is less than epsilon. Okay. Now, why is this true? So M is the what? It's the supremum, which is the least upper bound. So that means that M is greater than or equal to every element of f of x. It also means that anything smaller than M is not an upper bound, because this is the least upper bound. Okay. So the idea here is that you can sort of imagine that I wanted to claim there was some other there was some lower upper bound. So if there were going to be some lower upper bound, that would need to mean that sorry, let me phrase this a slightly different way. If I were going to say, if I want to say this is the greatest, sorry, I want to say this is the least upper bound, one way to phrase that is to say that if I looked at anything smaller than, back up. So to see why this is true, so we have M here defined as the supremum of f of x. That means M is the least upper bound. That means if you tried to take any other upper bound that was, if you tried to have an upper bound that was smaller than m, you couldn't do that because you would find some element of your set which was bigger than that smaller value. So if I look at this claim here, I could actually rewrite this as m minus epsilon is less than z. So the idea here is for any epsilon, if you tried to claim m minus epsilon, so that's something a little bit smaller than m was an upper bound, you'd have a problem because there's always going to exist something in your set that's bigger than that lower, that bound you're trying to take that's lower. So the idea here is there's always going to be something bigger than something in your set f of x that's bigger than anything that's smaller than m, because m is the least upper bound. So anything smaller than m can't be an upper bound anymore. All right. Another way we sometimes phrase this, although it doesn't come directly from the definition, but it's equivalent, right, is that this is an upper bound, or sorry, is a least upper bound because I can find things in my set that are arbitrarily close to this, okay? But what this means, right, if I look at this, for every epsilon there exists a z such that this, what this is really saying is, said another way, if I look at the neighborhood of radius epsilon around m intersect f of x, that is non-empty for every epsilon. So what we're really saying is that m must be an accumulation point of f of x. So since m is an accumulation point of f of x, then m, see, I think I can squeeze it down here, m is in f of x since x is closed. Or sorry, since f of x is closed. Right? So it's closed, so it contains all of its accumulation points. M is an accumulation point of f of x, and so we're done. Okay. Now, why are we done, right? If m is in f of x, that means it's in the image, right? So there is something in x that maps to capital M, and capital M is the supremum here, which is the same as saying the maximum here, right? We differentiate between supremums and maximums, right? Maximum is something that is achieved. Supremum is something that may not actually be achieved within the set. So we can actually say this is a maximum because it is in fact achieved on that interval at some point, and we just call that point x sub capital M. You can do something identical for x sub little m, but again, you're just using an infimum instead of a supremum. Okay, so again, to sort of review, the idea is you have this compact subset of your domain, you map it via f, that gives you a compact set. Because it's compact, it's closed and bounded. The boundedness gives you the existence of an infimum and a supremum. You can show that those infimum and supremum values of f of capital X are accumulation points of f of x. Because they're accumulation points of x and because they're accumulation points of f of x and because f of x is closed, capital M and lowercase m must be in little f of capital X. And because they're in there, that means there must be some values in the domain space, in the set X, that map to little m and capital M, which is precisely what you want for this generalized theorem. So we'll conclude the video here. In summary, what I wanted you to see in this video is that the extreme value theorem is, I don't want to say, we'll see later on why it's important. It's a very useful theorem, and we'll make quite a bit of use of it, improving other theorems throughout the course. But what I really wanted you to see in this video is that the extreme value theorem is an important result about continuous functions on compact sets. So as we saw, as we discussed a little bit in the last video, the intermediate value theorem is about closed and bounded intervals. We often show that, but really the more important piece there is the interval part, right? It's the fact that it's connected. That's the important piece for the intermediate value theorem. For the extreme value theorem, again, we often state it on a closed and bounded interval, but it's not the interval piece that's important there. It's really the compactness piece. It's the closed and bounded pieces that are important, not the interval pieces. So these two theorems that often in a calculus course we sort of quickly talk about as consequences of continuity, they are consequences of the fact that that function is continuous, but the issues that, or the hypotheses you need on the set in your domain are very different, even though we often state them as being for the same kind of sets in the domain. We often state them for closed and bounded intervals. The intermediate value theorem really uses the interval sort of essence or that connectedness, whereas the extreme value theorem really relies on the closed and boundedness of that or the compactness of that set. Again, if you go on and take a topology course, or maybe you've already taken one, but if you take a topology course, you would get a much more abstract take on all of this, and which would really boil down, those essential bits about connectedness and compactness. But for our purposes, we don't necessarily need that most of the time, but it is important to recognize exactly what properties of those closed and bounded intervals we're using in proving both of these important theorems.